Hello and welcome. In this video, I just walk you through the practical implementation of virtual sequence and virtual sequencer. And one interesting question, and the question is, if we have multiple agents, okay, in the environments. So for example, two agents we have right now. So all these two monitor have analysis port, or we can say a broadcast port. And if we have a single scoreboard, then how to connect this multiple monitor to this single scoreboard? We will try to see that, as well as the practical implementation of virtual sequence and virtual sequence. And here we are considering a DUT. In that, sub DUTs are there, like one adder and subtractor DUT, and we are considering two interface for them. Let me show you the code for that, and we will try to understand this complete diagram also, how to implement a virtual sequence and virtual sequencer. I will show you that in this video. Before that, let me show you the RTL for the adder and subtractor. So this is for the sequential adder, the RTL which is written in system Verilog HT. So as you can see, adder and module adder. Inside that, clock signals for adder, clock and reset, and two inputs A and B, and one output Y. So what we are saying at always underscore FF at the passage of this adder clock, if there is a reset, output should be 0, else output should be addition of these two inputs. Similarly, for subtractor model, inputs and outputs for that, and if the reset is equal to 1, the output Z of the subtractor will be 0, else the output will be subtraction of inputs M and N. Now inside the top module, just we have to make a connection. We have to instantiate our DUTs, adder DUT and subtractor DUT, and with the help of name-based instantiating, we have to instantiate the signals with this top module. Very simple. Now let me show you a simple interface. So we are considering two interface, adder interface and subtractor interface. So here just we need to declare all the inputs and outputs as logic. So inputs A, B and outputs Y for adder, and for subtractor inputs are M and N and output is equal to Z. Very simple. Now let me show you the top TB, where we are setting the virtual interface and making a connection with the DUTs here. In the module top TB, we are declaring the instances for two adders interface, adder interface and subtractor interface, two instances of interfaces for two different interfaces. Then in the top module we are instantiating here. Okay. Then within initial begin we are saying the clock, initializing clock is equal to 0, and here we are setting the virtual adder interface using set method of configuration database, as you are aware about this, and for subtractor interface also. So the arguments for set method is null, and we are giving the star so that all the components can access. And this is what the key for subtractor interface is: virtual subtractor INTF, for adder virtual adder INTF. And this is what the variable we are declaring here. And just we are calling a run test. So this run test is a global task defined in a UVM test in the UVM root. Okay, and we are just passing the test1 argument over here. Just we are generating a clock of 20 nanosecond period. Now let me show you the test bench architecture one by. Before moving to this, let me explain you the complete architecture of this DUT, which has two sub-DUT in it. So we have top, we just saw the top module. Inside that test we have an environment. Now environment has two agents, adder agent and subtractor agent. Both the agents are active agents, so both the agent will have all three essential components, sequencer, driver and monitor. And sequencer and driver connection we are connecting them using TLM analysis port and export in the connect phase of agents. And monitor has this analysis implementation port. So it is broadcasting this, or you can say the broadcast port. So now it is just sending this data to this scoreboard. So a scoreboard has this analysis implementation ports. And the new component, as you can find over here in the environment, is virtual sequence. And remember, as already I have explained in my previous video, the concept of virtual sequence and virtual sequence. Over there I said this virtual sequencer is a component, right? Mistakenly I said object over there. So it is a component in the UVM base class hierarchy, which holds the pointer for physical sequencers. So we have two sequencers, in agent one sequencer, and in subtractor agent we have another sequencer. One agent is in adder agent and one sequencer is in subtractor agent. So this two agent has two sequencer. So for that reason our virtual sequencer will contain two pointers for these two physical sequencers. Now let me show you the virtual sequence class. So here we are considering virtual sequence along with the virtual sequencer. Okay. So as you can see over here in this virtual sequencer, we have to define the sequence object of sequence classes. Then we have to declare two physical sequencer object. Then we have to declare the virtual sequencer, which has the pointer of physical sequence. And this M sequencer is coming here in virtual sequence with the concept of inheritance. We are not defining that. I will explain you in the code. Okay. So this is what the simple complete test bench architecture along with virtual sequence and virtual sequence. Now you can easily understand while we look towards the code. So for that, let me show you the complete code. First, we are declaring these two mandatory lines. So first line will give us an access to UVM macros. Another line, import UVM package, will give us the access to all UVM classes. Now here we are defining two transaction class. One is for adder and one is for subtract. So first is sequence item for adder transaction. Here we are declaring inputs as rand type so that we can randomize in the future. And we are declaring y as bit type. We are not randomizing. We are declaring the UVM object details factory registration macro along with the field macros so that we can use inbuilt methods. Print, copy, compare. And we are using one UVM decimal flag in order to print, if we want to print them in decimal form. Now this default constructor is expecting one argument as it is an object class in the UVM base class hierarchy. Now the next class is sequence class, which is also a a object class in the UVM based class hierarchy. So this sequence one is for adder, which is extending from UVM sequence and parameterized with the type of a transaction, factory registration macro and default constructor. Now inside the body, we are creating the object REQ, which is an inbuilt object of the transaction class using factories create method, and we are repeating 5 times. So now here we are not using start item and finish item. Rather than we are using tick UVM do macro. So this tick UVM do macro is capable of doing the 3 lines of code: start item request, finish item, and inside that it will randomize them. So we are using tick UVM do so that you can easily understand what is the use of tick UVM do. It is also one of the frequently asked interview question. Explain the functionality of tick UVM do and tick UVM do with. Just we are printing a message, data sent to driver using tick UVM info, and we are printing the transaction here using print method. End task body and end class sequence. Now let me show you the driver class, as it is also a parameterized class. Add a driver which is extending from UVM driver. Here we are getting that, declaring that interface as a virtual. Okay. So as you know that interface is an static component, and if we want to use them inside a classes, those the classes are dynamic, we have to make use of virtual, and we are declaring the instances via if. As it is a component class, it's factory registration and default constructor with 2 arguments. And in the build phase, first we are creating the object for this REQ request, which is an inbuilt object of the transaction class. And here we are getting that virtual sequencer which we have set it in the top using get method. Remember, this get method will return a bit type value, whereas the set method is a void method which will not return anything. So this get can return 0 or 1. If it is passing, can return 1, else it can return 0. But just we are using if not of UVM config db virtual interface. If it is not able to get that, we are making use of this. We are using tick UVM federal to print a message, unable to get virtual interface. And as get will also have 4 arguments: this first argument, empty double quote, and the key through which we have set it, and the variable VIF which we have declared. Now in the drive task, within the forever begin block, we are make using of sequence item port dot get next item and sequence item port dot item done. So I hope you are aware about the handshaking mechanism between driver and sequence. And with here just we are driving the stimulus to the DUT using virtual interface. First we are deasserting the reset. Then we are driving the stimulus using non-blocking assignment with the help of interface A and B. And just we are waiting for 3 clock cycles here. You can give any delay. So here I am repeating 3, so it will wait for 3 clock cycles. And just here we are printing that. Okay. Now in the run phase, just we are calling the drive task. Very simple. Now inside a monitor, which is extending from UVM monitor, it is not a parameterized one, hence we need to declare the object of the transaction class. Here also we are declaring the virtual for the interface. As monitor has analysis port, right? As we saw over here. So this adder agent has this analysis port. We have to declare that using UVM analysis port and parameterize with the type of a transaction. And the name is AAP. Name should be self-explanatory. So adder analysis port, AA. Now as it is a component in the UVM based class hierarchy, for that component factory registration macro and its default constructor with 2 arguments, and we are allocating a memory for this analysis port using the constructor inside this function. Now inside the build phase, first we will create object for this transaction class. Similarly, we'll get the virtual interface here inside this build phase of the monitor also, same as we get inside a driver. Now inside a task capture, inside a forever begin, first we are waiting for 1 clock cycle. We are checking if reset is equal to 1. So we are making the transaction reset is equal to 1. So we are updating the reset is equal to 1. And we are sending that to this analysis port of the model. So it will helpful in the scoreboard. So analysis, as you know, the scoreboard has the write method. So we are making using of that write over here. Now let me show you the else part for that. Okay. So if reset is not there, reset is equal to 0, then we are waiting for 2 clock cycles. Remember, already we have waited here for 1 clock cycle, and again we are waiting for 2 more clock cycles. Why? Because inside a driver, you remember we gave the delay of 3 clock cycles. So same we have to utilize in case of a monitor. As you remember, inside that driver, we gave the delay of 3 clock cycles. So here also inside a monitor, we are giving the same delay. First one is here and then 2 times here inside else part. Now here we are capturing the information using blocking assign. So as you can see, inside a trans object we are capturing through this virtual interface. So vif.a, b and y we are capturing inside this trans object, and just we are printing and we are sending that, we are capturing that information inside this write method of inside this analysis port with the help of write method. Now inside the run phase of the monitor, just we are calling that capture task. This is an agent class, agent config class. So here we can declare a parameter called UVM active passive enum is active, so that we are making the agent as an active agent. So active agent means it will have all the 3 essential components called driver, sequencer and monitor. If it is a passive one, then it should have only monitor. As it is an object class, we have to register with object details, factory registration and default constructor with 1 argument. Now the agent class, right? So adder agent, inside that we are declaring the instances for monitor and driver, and here only we are creating that UVM sequencer. Okay. So declaring the instance for config class also. Here I will show you inside a base test how we are setting the agent config. So we are getting here inside a lower level component called adder agent. And as it is a component class, factory registration macro and default constructor. Now inside the build phase, first we are creating the monitor, then the agent config class object using factory create method, and we are checking that if the we are getting that the agent config whatever we are setting inside a base test here, and we are checking that if is active is equal to UVM active, then only we are creating the driver in sequence. And inside a connect phase, we are checking that if the is active, meaning the UVM the agent is active, then only we are making a connection of the agent which has the driver which has a port dot connect to the sequencer which has export. So the connection is like agent dot sequence item port dot connect the sequencer export, sequencer object dot sequence item export. Very simple. Just we are ending a class agent. Now this second transaction class is for subtractor, which is very simple. Just we are changing the names of inputs and outputs. Same thing we are doing here. Then the sequence class is also same, just for transaction 2 we are making. And here also we are repeating for 5 times using tick UVM do. And the driver is also same, similar, just we are making it with the parameterized with the transaction 2 class. and same subtractor agent we are getting here. We are declaring for subtractor interface as a virtual, and so on. Similarly, same as that only. Here, similarly, the drive logic is also same. Just the inputs and outputs are changing. Okay. Inside the monitor also same thing. Just we are changing the parameterize class, and just we are changing the inputs and outputs. The logic is same as we have written for the adder driver and adder monitor. Okay, just changing the names only. So I'm not again explaining because it is same. And the agent class is subtractor agent. Same, just we are changing the name here. How we are creating them and how we are connecting in the connect phase. So as you can see, just let me show you the connect phase of the subtractor agent. So here the subtractor driver dot sequence item port dot connect to the subtractor sequencer dot sequence item export. So as you can see over here, subtractor agent, subtractor sequencer, we are making this subtractor sequencer and driver connection. The things are same.
Now the interesting thing is virtual sequencer. As
I told you, the virtual sequencer will contain a pointer for this physical sequencer. So as it is a component class in the UVM based class, we have to define like our own sequencer, virtual sequencer class name, extend from UVM sequencer, and we have to parameterize with the UVM
sequencer. And here we are declaring the instances or pointers for the physical sequencer. So as you know, UVM sequencer sequence item 1 is like adder sequencer. For adder sequencer, right?
For that we are declaring the pointer as adder virtual sequencer, and for subtractor sequencer we are declaring subtractor virtual sequencer. These two pointers will point to these physical sequencers. In the connect phase of the environment, you will find the object assignment statement. Don't worry about it. And just it is a container, so it will have the physical sequencer instances or pointers, you can say. And as it is a component, we have to register with tick UVM component details factory registration and its default constructor with 2 arguments. Now the interesting point is its scoreboard. So as you know, the scoreboard has 2 implementation ports, right? So how we are defining, and it is one of the most frequently asked interview question. And the question already I have explained. Let me again tell you the question. So the question is, if we
have 2 monitors inside of environment, 2 agents which has 2 monitors, how to connect those 2 agents with single scoreboard? We are trying to understand that. So as you can see here in the scoreboard class, top of that we can declare 2 implementation port. How to declare that? Using tick UVM analysis implementation underscore declare. In the parenthesis, 1 is for adder, 1 is for subtract. And we are making using of this inside a write method also. Let me show you how. So this is a simple scoreboard extending from UVM scoreboard. We have to declare the instances for the transaction class like sequence 1 and sequence 2. Sequence 1 is for adder and sequence 2 is for subtract. Here we have to declare the UVM analysis implementation ports of this scoreboard. So this UVM analysis implementation underscore add we have to be over for adder, and underscore sub for subtract. And as it is a parameterized one, first parameter is the type of a transaction, and second is where the implementation detail we are declaring. So implementation detail we are declaring inside the scoreboard itself. So the second argument should be scoreboard, and the name for that adder analysis implementation code, subtractor analysis implementation. Simple. So with this declaration we are declaring inside the scoreboard. Now as it is a component class, we have to register the component it is, and its default constructor with 2 arguments, and here we are creating or allocating the memory for this implementation. Now inside a build phase, we have to create we have to declare the object for memory allocation for these 2 objects of transaction classes, data1 and data2, using factory spirit. And this is a bit interesting. Write method, as you know that in the scoreboard has a write method. So that write method we are declaring for adder, so underscore add, which we have declared using pick UVM analysis implementation declared for adder and for subtract. So we are writing 2 methods here using add and subtract. So this is a void one, and here we are just printing the message using print build method. Data received from adder monitor analysis code, and we are writing the logic over here. Implementation detail. How we are saying? We are saying that if A is greater than equal to 0,
B is also greater than equal to 0, and we are checking if Y, the output, which is equal to addition of 2 inputs A and B, then test is passed, else test is failed, and print that. Else meaning if the A and B are unknown or high impedance, then just return or exit from this write method. Okay, exit from this write add method. Similarly, for write subtractor method, here also we are writing that logic mnn greater than 0. Then if output z is equal to subtraction of this mnn inputs, then test is passed, else test is failed. Very simple. If unknown or z value z, just return from that subtractor write method, and the end class is scoreboard. Now the environment class. Inside the environment, as you know, we have the scoreboard. Here is scoreboard. We have 2 agents and 1 virtual sequence. So we have to declare all 4 here. Okay. Then inside, as it is a component class, factory registration macro component and default constructor with 2 arguments. In the build phase, we have to
create all these 4 essential components, whatever we have declared using factory's create method. Now inside a connect phase, this is a bit interesting. Inside a connect phase, what we have to do, we have to connect this analysis port of this adder agent with analysis implementation for both of this is code, and analysis port of this subtractor agent with analysis implementation port of this is code. And we have to make use of
object assignment statement so that this sequencer object, those are there in the virtual sequencer, will point to these physical sequencers. So we are making a connection here. So the analysis port of a monitor, for example, this agent monitor analysis port. So agent object dot
analysis the monitor dot analysis port dot connect. Inside a scoreboard, we have this analysis implementation port, right? Adder analysis implementation. We have to make a connection in this. Now here, the subtractor agent has this monitor which has analysis port, which we have to connect with this scoreboard analysis subtractor analysis implementation port, which we have declared already inside a scoreboard. So we are connecting here inside the connect phase of this environment. Now this is important, the object assignment statement. So with this, what happens? What we are doing, the objects, those are there in the virtual sequencer, will be point to the physical sequencer object. Okay. So for that, how to write the object assignment statement? The virtual sequencer which has adder virtual sequencer, the pointer for this adder virtual sequencer should be point to this physical sequencer which is there in the agent. Okay. So how to write the virtual sequencer which is there in the virtual adder virtual sequencer which is there in the virtual sequencer will be point to this physical sequencer which is there in the agent. Similarly for this. Okay. subtractor agent. How to write that? The virtual sequencer object has this subtractor virtual sequencer which is there in the virtual sequencer. Okay, so this object virtual sequencer, subtractor virtual sequencer, this which is there in the virtual sequencer, will be pointing towards the physical sequencer which is there in the subtractor agent. So with this subtractor has this physical sequencer, and this virtual sequencer has this subtractor vir sequencer. So with this object assignment statement, this will point to this physical sequencer which is there in the subtractor. So very simple, you can understand with this green line. Now let me show you the base test. Inside the base test, what we are doing, we are declaring the instances for the environment and the config class. As it is a component class, we have to register component details and default constructor with 2 arguments. And this config class we are setting here agent config in the build phase, right? So inside the build phase, first we are creating the environment object and the agent config object. And we are setting that agent config here, agent configuration. Now in the end of elaboration phase of the test, this base test, what we are doing, just we are printing a topology in order to check what all components are created. Inside the report field, just we are saying that if the svuvm fatal plus svuvm error greater than 0, then just say test fail, else test false. Very simple. Now this is the interesting class called virtual sequence, and we are considering this virtual sequence along with the virtual sequence. Okay. Let me show you that. So as you can see, inside the virtual sequence, we are declaring 2 instances of sequences and physical sequencer objects and one virtual sequencer object. Okay, let me show you those things. So first virtual sequencer object, then 2 sequencer object, this and this, and objects for this instances for this sequence as you can see over. As it is an object class, we have to register with a tick svuvm object details factory registration, and its default constructor expecting 1 argument. Now inside the body method of virtual sequence, we are creating the object for these sequences allocating a memory using factory's create method. And first we have to do a $cast between virtual sequencer object and m sequencer. Remember, this m sequencer we are not declaring, it is coming through the inheritance also. So we are doing $cast between this. With this $cast, let me show you what this $cast will do. So this we are doing $cast between this virtual sequencer object and m sequencer. So with this virtual sequencer will pointing towards the m sequencer. So after executing this, what will happen? The m sequencer will internally pointing to this virtual sequencer which is there in the environment. Okay. Now here we have to write 2 object assignment statements. So what are those? What we are saying, here we are declaring these instances for physical sequencer, right? So we have to make them to point towards this virtual sequencer which is there in the virtual sequence. Okay. Now how to do that? We have to write the object assignment statement like the sequencer object which is there in the virtual sequence. So the sequencer object, these 2 sequencer objects, those are there in the virtual sequence, should point to the virtual sequencer object which is there in the virtual sequence. Okay. So for that we have to write the physical sequencer object will pointing towards the sequencer object, those are there in the virtual sequence. Let me again tell you. Also, the physical sequencer object, this 2 which is there in the virtual sequence, will be pointing towards the virtual sequencer object of virtual sequence of this object assignment testing. And here just we have to start this sequence onto this sequencer object. So how we are starting? The sequence 1 dot start onto this sequencer object, and after delay of 10 time unit, we are starting this sequence 2 onto this sequence object which is there inside virtual sequence. Very simple. And just we are in task body and end class virtual sequence. Now inside test class, test1, which is extending from base test, we are declaring the instance of virtual sequence. And as it is a component class, component registration method, take your game component to some default constructor with 2 arguments. And just we are calling the build phase. So this build phase parent we will call to the parent build phase, which has the corresponding logic for config DB and creating the environment. And here in the run phase of that, just we have to create the instance for virtual sequence using factory create method. And just we have to call phase.raise objection and drop objection. Inside that, just we have to start this virtual sequence onto this virtual sequencer which is there in the agent. Very simple. So what we are doing, we are starting in the run phase of the test and we are starting this virtual sequence onto this virtual sequence. And as you know, this already we have made the connection of this using object assignment statement. So the virtual sequencer has this 2 pointer of physical sequencer which will point to this physical sequencer object. So at the end, what is happening? We are starting this sequence onto this sequencer object which is there in the virtual sequence, and those are starting onto this virtual sequencer. And this virtual sequencer which is there in the virtual sequence, we are starting this virtual sequence inside this on this virtual sequencer which is there in the environment. Very simple. So by this
following path, we are starting this sequencer onto this sequencer which is there in the agents of the environment. Very simple. So remember once again, we are starting this virtual sequence onto this virtual sequencer which is there in the environment inside this run phase of the test. Okay, using start method, virtual sequence dot start onto this virtual sequencer which is there in the environment. And already I have explained this internal paths, okay, to you so that you can use it. So at the end, this sequence will start on this virtual sequencer which is there in the virtual sequence, and we are starting this virtual sequence onto this virtual sequencer which is there in the agent. By following this internal path, at the end, this sequencer will start this virtual sequencer object will point to this physical sequence. So we are generating a sequence here and we are starting those sequence onto the sequencer using this internal path. Very simple. And already I have explained this top model. So let me run this code. So that you can easily understand the output. First we will understand the topology and then we will see whether the test is passing or not. Just we will compare the display from the scoreboard so that we can easily understand whether the test is passing or not. So the test is passing. Let me just show you once. So for example, if you just analyze, let me show you the topology which we have printing from the end of elaboration page. So this test is the top one. Inside that environment is the adder agent. Then we have which has driver, monitor, and sequencer, right? Then we have a scoreboard. So the scoreboard has 2 analysis implementation port, right? Add and subtract. and the subtractor agent which has subtractor driver, subtractor monitor, subtractor sequencer, right? Then we have the virtual sequencer, okay, and so on. Just let me show you the transaction, how we are generating sequence 1. So for example, this sequence 1, okay. So here you can see A is 14, B is 13, and inside a driver, if we check that, we'll find A is 14, B is 13. Inside a monitor, same 13, 14. Inside a scoreboard is 13 and 14 is equal to 27. Hence the test is passing, right? Now let me show you one is from sequence 2, and you can play with this code. Let's try to check the subtractor also. Okay, so this is sequence 2, which is for subtractor. Okay, so inside this M is 3. Let me show you. Subtractor. Okay, so let me show you this sequence only. M is 2, N is 0. Okay, so inside the subtractor driver 2 and 0, and inside a monitor 2 and 0. Inside a scoreboard 2 minus 0 is 2. Okay, and test is passing. So you can play around with this code and you can try to explore it more. So with this, I hope you have understood the practical implementation of virtual sequence and virtual sequencer. Also that question that if we have two monitors inside our environment, how to make the connection with a scoreboard, single scoreboard. And already I have posted a video of virtual sequence and virtual sequencer concepts. So before proceeding to this, I request you to go through that video once so that you will find this implementation code easy to understand. Okay. So with this, I hope you enjoyed this video. So thanks for watching. Thank you.